introduce Randy really briefly. He doesn't need a whole lot of introduction, but Randy is now a project scientist at SLAC at LCLS, battling all kinds of fights with users, demands, schedules, real life. But he's been kind enough to volunteer to give us a rundown on one of the main aspects of his PhD. Is not the only thing that he worked on. Primarily, he's been working on structural photonics and kind of light shaping in both space and time domains. But it would be important for all of us to consider what it means, the early work that we've done in the group on UV shaping, and in particular UV shaping for LCLS2, which has a very specific parameter set. As you'll see, this is very important for Lingshan and specifically how, and definitely links with Jack's work, right? But you'll see that Randy will talk about regime, which is in the several picoseconds to tens of picoseconds, in which shaping is really non-trivial. So I think with that, Randy, I'll let you just present, and you let us know how you want us to organize this. If you want to have any of us interrupt with questions and wait until the end, it's up to you.
Yeah. Anytime there's questions, either raise your hand or just say, excuse me, or something like just speak up. I'm good with any of that. I think keeping it a little bit more natural rather than you know, formal and waiting till the end will actually help a lot of the understanding of it as well. So seeing it fine?
Yep, thank you.
Excellent.
Take it away.
Yeah, so like Sergio said, basically I want to talk mainly just about some flat top UV shaping that was a large part of my thesis at sector 0, which is the injector, the beginning of the LINAC at SLAC. This presentation was given kind of originally. I modified it a little bit, but not too much for the folks at SLAC. So some of the background of what is and around there may not be there. But LCLS2 is the giant accelerator for superconducting that's starting up to back the X-ray, the X-ray generation in the undulators, the free electron laser. So as part of that, at the beginning, there we go. At the beginning of any of these electron accelerators, LINACs, FELs, etc., for electrons, you're going to have the photocathode. And this is typically some sort of metal, semi-metal, where a laser is incident on it. It releases electrons with the photoelectric effect. Those are accelerated in a radio frequency field, focused with lenses, and they continue onwards. This is fairly simplified dynamics. You guys have your own injector, well, DC gun out there. But it's all fairly similar as to how it works. You would have a DC field instead of an RF field. However, the electron beam performance that comes off of the cathode, that is how they form in space and time, is very dependent on the laser shape. The temporal profile and spatial profile, it more than informs the electrons, it basically determines how they form. In general, for XFELs, X-ray free electron lasers, you are wanting something that has a pseudo flat top laser profile with a smooth you don't want the intensity fluctuations long. You want it to be a smooth change from beginning to end. The reason for this in XFELs is that generally this sort of profile minimizes the space charge forces from the electron beam on itself, or it linearizes them, I should say. So instead of having some sort of nonlinear space charge forces, if you can get a uniform distribution of your electrons in space and time, then you end up with linear space charge forces. And those can be compensated with electron optics later in a simple format, whereas nonlinear forces can't be. LCLS2 in particular is asking for 20 to 60 picoseconds flat top in the UV. We're shooting for 267 nanometers, the fourth harmonic of 1064, which is kind of, I think the Ferros is 1064 as well. So it would just be that, except instead of your OPA, it's just quadrupling, going through doublers twice. In general, the laser shaping in injectors is what's considered the easy avenue forward towards achieving these high fidelity, low emittance electron beams that can be used to get really high energy X-rays and really powerful. So high energy meaning per pulse, and powerful, the average power over time. Yes, so
Briefly about why you get higher brightness in an exfil? How is brightness related to emittance? Just so I have
Yeah, sure. I don't think I have any slides in here with like the equations. I can pull them up maybe at the end if we just want to see it in my thesis. But basically, when you create your X-rays in your undulator, you take your electrons, you send them through this oscillating magnetic field, north, south, and it just flips. When your electrons travel through that, they wiggle at some specific frequency. Having a low emittance generally means that your electrons are all traveling in the same direction at the same speed. It can more or less be thought of it like that. And so when you have these low emittance electrons, you better match your condition basically in the undulator. You're able to actually have more electrons that are oscillating at the exact same frequency at the exact same time, and they're also compressed in time. So you have this very short electron bunch, femtoseconds, attoseconds long. All of them are oscillating at the same time. And when they do that, their emission is coherently adding and creating X-rays. So the lower emittance that you have, the more you can get them in phase with one another, and actually creating these X-rays all at once and getting your higher brightness beams. The other aspect of it, so that's like the power of it. You can also get to higher energies, higher photon energies with your electrons. I will admit, maybe off the top of my head, I don't remember exactly why. I know that where it comes in the equations, but I'm not remembering why in the undulator you actually can achieve the higher energy X-rays themselves. I think it's just because you can accelerate to higher gammas. Basically, your electrons can move faster in time, and that kind of directly correlates in there.
Yeah, it's along those ways. It has to do with the FEL can afford a delta E of tall like before it can no longer lays, and so the delta E becomes more stringent the higher the electron beam energy. So you need to keep your emittance low. So at some point, if your electron beam is too broadband,
Yeah.
your FEL won't lays.
Delta E in this case, for those who don't know, is basically your center energy of your electrons, their kinetic energy over how broadband your whole pulse is, your electron bunch is. So if they're all very very low emittance, they're all similar in energy. So your delta E is very small. So yeah, that's kind of why you want to have these really high quality electrons coming off the cathode, and that's this sort of laser profile allows for some of that, and it allows for compensating for drifts with electron optics instead of it just being this uncompensated mess. So that is kind of some background on the injectors of XFELs and why you might want to be shaping your laser, particularly in time. I don't do a lot of talking about space in this one. It's mainly in time. So with that said, how can we actually achieve this profile? Because in the UV and at 20 picoseconds, this is a very complicated thing to do. If you were just to try to do this with a 20 picosecond laser, you would have a very narrow band laser, and so you wouldn't be able to do a lot of the traditional shaping elements, like spectral shaping, phase, or amplitude. And the picosecond regime is faster than any sort of electronic response that we have, and so you can't use direct shapers. So this is just an area, femtosecond, you can use spectral methods, nanosecond, you can use temporal methods, picoseconds, awful, and there's nothing really that directly works in there. So we got to find a way to actually shape in this regime. And that's where the method that we developed came up with comes in. So the idea is that you take your IR beam, your 1064 beam, you split it in half, so equal power, and you actually apply a negative chirp and a positive chirp. Now, should probably actually cover a little bit of that. So spectral chirp, when it comes to ultrafast optical pulses, you can represent the spectral phase. So that's basically the time delay of each of your different wavelengths with a Taylor series about your central wavelength. If you have a Gaussian profile in your spectrum, then it works really well. And you just take a Taylor expansion around your center frequency, and your phase is more or less the time of arrival of each of your different colors in your pulse. So with that, what we are focusing on is the fourth order of your Taylor expansion, which is, so 0 is just time delay. First is complicated, it's carrier envelope phase. So had those two backwards. We don't really focus on those too much. Second order is basically a linear delay in time. Third order is a quadratic delay in time, which is kind of complicated to think about, but generally all you need to know is that second order dispersion or chirp, I'll use these terms very interchangeably, stretches out a pulse in time. If you have a femtosecond pulse that has some sort of broadband spectrum and you apply second order phase to it, negative or positive, it just stretches out and looks Gaussian, but it's longer. Third order, you actually end up creating these sort of pre-pulses or post-pulses and really creating this sort of tail off to one side or the other. Third order is an odd function, which means that your negative and your positives have different effects. So with that said, we take our two pulses, split it in half for power, apply negative chirp to one side, positive chirp to the other in equal and opposite amounts. So they both roughly look like triangles. Mix them in this non-collinear sum frequency generation. It's sum frequency because one is ordered blue to red and the other is red to blue. Inside your pulse spectrum, you only have like a few nanometers to work with, but that's the colors in there. And then what you get out is you get your second harmonic generation of these various pulses. And these are parasitic processes. You really just end up throwing these away. But in the sum frequency generation in the center, you end up with this sort of profile. Now, straight out from this process, all of these intensity fluctuations result in this very kind of ugly looking pulse. But the general shape is there. We can see that this roughly looks flat top, but it's very highly oscillatory. Now, the spectrum on the side of your sum frequency generation pulse is also very highly oscillatory and has this sort of tail of high frequency components that go off to one side. So if we can actually apply a spectral filter and get rid of those high frequency components, but keep most of our main content in this like very strong center peak, then we can actually flatten out and get that background shape that I was talking about before. So with this way, negative positive chirp, non-collinear sum frequency generation, second harmonic is parasitic, but the sum frequency comes out. It's very highly oscillatory, but then we spectrally filter that SFG pulse, and you get something that's roughly flat in time. So this is kind of how a diagrammatic thing of this whole setup would go. Start with 1064, shape it, convert it, filter it. Now you have this smooth profile in the green. However, because you have this smooth profile in the green and you've mixed red and blue in opposite sides of your spectrum as you go along, the spectral content of this is no longer Gaussian like you would see if you just normally converted your pulse to second harmonic generation. Instead, it's this very, very narrow band, nearly transform limited. And because it's nearly transform limited, the phase is flat because we've mixed equal and opposite amounts. You can directly convert to the UV without ending up with any sort of fluctuations because of your phase mismatches or intensity mismatches and stuff like that. So with that said, this sort of process, we investigated this in theory quite a bit. And just to cover some stuff here, I don't expect anybody here to really be able to read. Well, maybe Sergio, you should be able to read these graphs directly. But what we did is we simulated creating electron bunches at the photocathode for LCLS2 with a Gaussian profile, and then with that square DCNS profile that I was just showing. On the left here, this is the transverse emittance of the electron bunch right at the end of the injector. So they've already been accelerated a little bit and they're traveling out in space. The main takeaway is that DCNS, that square profile for pretty much any bunch length, so the amount of electrons you have, reduces the general transverse emittance that you're seeing in that profile. It creates a much more well-behaved, much more linearized space charge force beam. As we take that bunch and we propagate these down the accelerator, the Gaussian and the DCNS pulse produce generally the same electron energies because they're going through the same type of accelerators, but the peak current that you see here is much higher, almost 2 times higher for DCNS, which just means that you have a lot more of your electrons actually able to be compressed into a short period of time. Your current is higher, current being your charge over time. So shorter time, same amount of energy, higher current. And then the bunch just before the undulators. Now, both of these look kind of complicated here. The main point is that we actually have the similar peak currents among both of them and similar energies. However, this flat part in the center here for DC and S is much easier for the undulator to produce X-ray radiation with than anything that you're seeing up here in the Gaussian. Now, the Gaussian has this flat profile a little bit, but it's on one of the sides of the tail as opposed to where you have a lot of your electron bunched together. So really, DC&S is able to produce an electron bunch that has a much flatter energy profile across the bulk of the electrons than trying to just do it on one tail or the other. And then if we look at the X-ray buildup with those, the pulse energy that you're able to get with our DC&S profile over here is significantly higher energy than the Gaussian. You know, and this is just supporting a lot of what those initial assumptions we made about the profile of our UV. So I'm gonna stop here for questions. Anybody have anything? Because this is all the theory behind it before I go into how we actually did the experiment.
Wait, yeah.
Yeah.
What's the rep rate then? Because your current is like charge over time.
Yeah, so what we're talking about here is actually the this is a per pulse current, not necessarily like a rep rate, like an average current. This is just a peak current within the pulse. And so each of these electron bunches is only a few picoseconds long, or tens picoseconds long.
Okay, that makes sense. Thanks.
Yeah, like tens of picoseconds, but also like hundreds of picocoulombs, maybe tens of picocoulombs at that point. So, your current, everything kind of balances out to be amps there. Any other questions about any of the DC&S specific stuff or anything like that?
What's the duration time of the IR for the input? Oh, it's around 20 picoseconds.
Yeah. So this whole process, before we even shape the pulses, right? We can start with just transform limited IR pulses and split them in half. And then when we stretch them out in time, each of these out here is probably, full width half max is a better descriptor of this because you don't have a 1 over E squared, you don't have a Gaussian distribution, but they're about 30, 32-ish picoseconds in time, full width half max. But you can see this is our halfway point-ish. There's still quite a long tail off to one side. However, when you mix them together, they're only going to produce light where they overlap. And so you can control a lot of how long your pulse is because you have this really sharp rise and fall on them. And so if you actually pass them in time past each other, if this one has a long tail, but it's not at all overlapped with anything from here, you're not going to make SFG, you're just going to make SHG. So you can control a little bit of your time duration just by sliding these over one another. But they're about 35 picoseconds here to make 20 picoseconds in the UV.
Oh, I see. Thank you. So, is that possible that the duration time of the green light, the green light, the duration of the green light be controlled by tuning the delay of the two IR of input?
Yes, yeah, it's not perfect though. Like you can't just slide the IR over one another and expect to keep the same profile here.
Okay.
You'll end up getting different oscillations, fluctuations, and everything here, but more or less, yes, you can control some of that stuff. It's not ideal.
So,
if you're wanting to change the green profile here, it would be better to keep the same time delay, but change your spectral phase that you apply to the IR. So apply more or less phase so that your center wavelengths are still stacked up on top of each other in time, but then all of the side wavelengths stretch out or compress in time relatively.
Okay, I see. It's more. I think it's more complicated in when doing the experiment. Okay, I see. Thank you.
Yeah. I mean, in theory, really simple. You just apply a little bit more or less phase, and you can really change this profile over here. However, yeah,
I can see
doing that, applying that different phase is really challenging. One of the things is like this regime of tens of picoseconds is a lot of phase when we talk about femtosecond pulses, right? Like, for somebody's trying to make a really short femtosecond pulse, they care about thousands or tens of thousands of femtoseconds squared of phase. If you notice here, we're applying 3.2 picoseconds squared, which is 10 to the 6 higher. So like, this is 3.2 million femtoseconds squared, which is a lot when you think about femtosecond optics, but at the same time, gratings and things like that will add hundreds of picoseconds squared with only a very short propagation distance. So it's kind of hard to actually achieve some of this delay here.
Okay, thank you.
I want to say something really briefly, just to not, I think you're doing a good job, Randy, but just to make sure that this concept is not undersold.
Yeah.
Just to put it really simply, whatever, forget about third order dispersion, whatever amount of chirp you add to the red pulses, for example, in China, if you add 20 picoseconds, if you stretch the red pulses to 20 picoseconds, your green is going to be approximately 20 picoseconds, with a caveat that it's transfer limited. It goes from pulses like yours in the lab that are nanometer bandwidth to picometer bandwidth automatically, and I think that's an easy thing. And you said it, Randy, but it's an easy thing to skip. And so basically how long or short your SFG pulses are depends on how much chirp you add to the red. If you want to add a nanosecond, you end up with a nanosecond. There's some caveats here in efficiency and what have you, but that's a trick. And then he is just focusing on this flat top because LCLS2 and how you're gonna hate this. It's flat top, flat top, flat top, flat top, and more flat top, just forever and ever again, right? But if Randy changes the ratio between SOD and TOD for it to be not necessarily equal but different, or not necessarily opposite signs, you start playing with that shape. So there's two take-homes from this technique. Is that one, you go from broadband to narrowband, from broadband to extremely narrowband to transfer limited. And second,
the extremely narrowband is super useful in further nonlinear conversion experiments or any sort of nonlinear process, because then you can stop worrying about some of the phase effects and things like that, phase mismatch.
Yeah.
Sorry, I just want to highlight why that's important.
And then you can play with SOD.
Oh, he's gone.
Looks like it.
All right. Well, I think I know the point he was going to make there. You can play with SOD and TOD in varying amounts to actually change this profile on the outside. Here we have equal and opposite amounts of second and third order. So, this one is negative second, positive third. This is positive second, negative third. If we still kept negative and positive second order dispersion, so that they're still ordered roughly linearly oppositely, one's red to blue, the other's blue to red, but we had the same sign of third order dispersion, you'd actually end up with two triangles that are facing the same way in time, but one of them has its frequencies opposite of the other. When you mix those together, you then end up with a triangle over here as well, roughly. Like, this is all kind of speculative. So the process I'm talking about in this talk specifically, very focused on flat top. The process in general, with changing your second and third order, you can create almost any profile over here, as long as it kind of obeys the laws of like the superposition of waves. Like it's very powerful. You can create a lot of different shapes, but you have to just play with your phase over here in order to do that. I'm just gonna Slack him in case he probably knows.
Wait, one last question. Sorry, I have one more
Yeah,
question.
go ahead. No, I'm just getting questions.
So how broadband does your initial IR need to be? Like, is there a minimum or like a maximum, or
yeah, so great question. The more broadband, the better generally. The more broadband your initial pulses are, you basically have more wavelengths to add and subtract phase from. You can be a little bit more discrete with your shaping. The more narrowband you get, you kind of just you basically start going to where you're just doing variations on a Gaussian. The more broadband, you can really get some crazy shapes in there. The other thing is this parameter alpha here. This is a number that I use in my thesis and stuff like that to talk about the ratio of second to third order dispersion. Well, technically third order to second order dispersion, third order is on top. And this parameter here allows you to actually have similar shapes with various bandwidths. If you have the same rough amounts of second and third order in proper ratio, but larger bandwidths, you end up with just the same shape, but stretching out in time. So, any other questions? All right, cool. Well, Sergio's seen it all before, so we can go on and he can come back with any other comments he has. So the experimental demonstration. So this is taking all of that diagram I was just showing you and actually putting it into practice. What I'm showing here is the end of the laser table at sector 0 at LCLS 2. There's 2 laser tables here, and there's another 4 beyond it that take up the operation side, and the 2 that I have were the R&D side. We use a light conversion carbide. It's very similar to the ferros that you guys have there. 1024, 246 femtoseconds, 40 watts from 100 kilohertz to 1 megahertz, so that your pulse energies can change. All of my stuff I did at 40 microjoules, which is either 40 watts to megahertz or, you know, less power at whatever rep rate. I wanted to keep my pulse energy the same. That way all the nonlinear dynamics were the exact same going through the crystals. I didn't have to worry about differing pulse energies and stuff like that. My fluence basically stayed the same. And then the ideal parameters that we have on the outside, the UV 257.5, which is just the 4th harmonic of that, 20 to 60 picoseconds. Here, because changing your phase is so complicated, we really are just searching for 20 picoseconds. And then we want 3 microjoules in the UV. So that's, you know, at a megahertz, that'd be 3 watts and changes from there. And we really want to achieve that non-oscillatory and flat top intensity profile. So here's the system design in a little bit prettier format than trying to label things on a table. We come in with our transform limited pulses over here on the left, and we leave with our UV on the right. We split it in a beam splitter. Half travels to the stretcher, half travels to the compressor. Each of these 2 devices, the stretcher and compressor, are a matched pair. So they produce the exact same but opposite sign. So same magnitude, opposite sign amounts of second and third order dispersion. There's a little caveat here. We're trying for 2.56 picoseconds with our actual laser instead of simulation, and 0.28 picoseconds cubed third order, which is a slightly lower alpha than we saw before. But the caveat here is that the I had a couple more slides in here. So assuming that we go through all of this, and I'll talk about the chirp volume Bragg gradient, which comes in later, all of this left side allows us to actually get to this second and third order dispersion values. The next part is the actual frequency conversion, which is we get them aligned in time and space, send them through a lens into BBO1, do our sum frequency generation here. This is a cylindrical lensing, because when you have 2 circles that are crossing at an angle to one another, it actually looks like an ellipse. The cross section does. So you have to do a little bit of cylindrical lensing in order to get it to go back to circular. Our spectral filter to take out those oscillations, and then back to the UV. So like I was saying, the stretcher and compressor are matched designs. We come in with this really short, if these were on the same scale, this would look like a delta function. But we come in with Gaussian and come out with our triangular looking pulses. Because like I was saying earlier, it's very hard to achieve the amounts of dispersion that we're looking for here. What we actually did is we have our stretcher and compressor designed to give us significantly more, about an order of magnitude more dispersion in our second order dispersion, but the proper amount of third order. So after traveling through the stretcher and compressor, the various pulses are oppositely ordered in time, red and blue, blue and red, but they have the right amount of third order dispersion. So they have the right tail on the various sides, but they're very, very long in time as opposed to being the proper amount. And so one of the very key things that we have to do with this, though, is that they have to be exactly matched to each other. If we have differing amounts, different magnitudes of our second and third order, our pulse shape starts changing. In order to do that, we take the output of the compressor, pass it through the stretcher, and then measure an autocorrelation. So ideally, these are matched together. If we come in with transform limited, go through both devices and come out, we should have roughly our transform limited femtosecond pulse, because we haven't converted anything yet. So we're still in the femtosecond regime. After the two of them, we get 422 femtoseconds. This is, almost a factor of 2 longer than what we get as an input. We do lose some spectrum in our stretcher. So, we're just losing some information there. We end up with a longer pulse because of it. But if all of this stretching here was second order only, it's only about 0.03 picoseconds squared, which is 1% of what we hope to achieve at the end. So even though we don't end up with a totally transform limited pulse here, we are still in a good shape to do the proper shaping. And the last element that we have for our phase shaping is what I was talking about earlier, which is the chirped volume Bragg grading. So in this case, our compressor line comes in from the left here and then reflects out. The different colors reflect at different depths. So red, green, blue, all reflect at different depths in there. You can think of it as basically a selective mirror that's based on your wavelength, where they reflect based on how far along in this crystal or optic you are. However, if you come in from the opposite side, like the stretcher, then your blue reflects first, then green, then red. So in this way, it is almost a purely second order device. You really end up with a linear ordering of your wavelengths as a function of depth. And so if we come in with our really, really stretched pulses, they're hundreds of picoseconds, pass them through this device, then at the end, we're left with the proper amount of second order that we're hoping to get. We had a lot more second order in our stretcher and compressor, the proper amount of third order. CVBG is an ideally second order device, subtract it off, and we're left with exactly what we want to get. 93% diffraction efficiency in this for those who care about those things, kind of more of an engineering side of things. So with that said, after our compressor, stretcher, and CVBG, we have basically the pulses that we're looking at on the left over here. Your negative and positively chirped pulses with the different tails. We don't have a cross correlator for IR, so I don't have like a profile of our IR. However, if we just take this into the green and we start trying to look at what we're able to produce, we can see here that we create our second harmonic generation pulses on the left and right. This is a true color image, by the way. This is the color of 515 nanometers or 512 nanometers. And then in the center here, you have your some frequency generation pulse. There is a little bit of ellipticity to it. However, we get really good conversion efficiency. When we're optimizing purely for conversion efficiency, that drops when we start optimizing for profile, for shape later. But right now about 30%. And our SFG pulse in the center here is still very, very Gaussian in its spatial profile, which is important for the electrons later. It creates a very uniform emission. However, the ellipticity is there, so that's why we have those cylindrical lenses in. And the other thing is looking at the spectrum of the green, we can see that we actually end up with a really large compression, bandwidth compression. If you look here, there's like this background that's beneath the peak that goes from about 510, 510 and a half to 514-ish nanometers. Those 4 to 5 nanometers is actually the spectrum of our SHG pulses. And our SFG only has 3 or 4 points that fully describe its peak, which means that we really are at the resolution limit of our spectrometer. Likely, our spectral bandwidth of our SFG is even shorter than this, but we don't really have a good way to measure it. So with the delay stage, to make sure they're lined up in time, we can actually roughly get an order of magnitude measure of how long our green is, which is about 33 to 50 picoseconds. In time. So each of our IR pulses up here is almost bang on where we want them for duration. Again, we don't have a direct time measurement in the green or the IR for these, unfortunately. But because we know that we have this bandwidth compression, we know that we have this very flat phase, we can just take it to the UV and measure it there. So this is the initial profile that we were able to generate in the UV with this process. We have about 26 picoseconds full width half max, very quick rise and fall times. However, we're still seeing these large intensity fluctuations, and these fluctuations are not just artifacts of the setup, they really are there because any sort of realignment we do, they persist. They are a fundamental fact of our light. It's not like we have a misalignment somewhere else. Spatial profile, still really great though. The reason that we have this sort of intensity fluctuations, we spend a lot of time searching for where this could be coming from. It turns out that if you actually do spectral filtering, not only in your green, but in your IR, and you actually clip part of your spectrum here. So red is what's reflected. Remember, reflected is the type of beam that we want. Our reflected beams actually end up losing some of this red wavelength. So the spectral information, this content that we need. The transmitted gray here is just lost power. It's not something that we can get back on our system. And this is just mainly due to a difference in the design of the CVBG versus what was delivered, more or less. It's just off by enough that we end up losing some of this red content. And when we lose that red side of the spectrum, what happens is that we get in simulation these profiles here. So we go from this flat top in time to having this slow fluctuations as opposed to the very fast ones we saw before, but it's still there. It's fluctuations that we can't get rid of. In order to compensate for that, we just added a bandpass filter and cut out some of the blue side of the spectrum. So we basically symmetrized our cutting of our spectrum rather than losing just one side. Now we're losing both. But Linshan, this is basically what you were talking about earlier. If we cut our bandwidth, right? If we cut our bandwidth, but our phase is the same, then we can have a similar profile, but it just changes in time. And with that, we actually get this profile here. So we end up with that sort of flat top that we're seeing. There's still a little bit of inconsistencies, but for a proof of concept, it's definitely there. But we went from 26 picoseconds to 19.8 picoseconds. So we cut out some of that bandwidth that we had before with the same amount of phase, and our time of our pulses actually decreased a little bit. All of what I've shown in here is at 250 kilohertz and 40 microjoules in the IR. And then just really quick, we took this profile and simulated an electron bunch generated with this and saw how it performed in the injector. We didn't have time to take it all the way down the accelerator and the undulator because that's a very expensive calculation. But what we see is that with this profile that we experimentally generated, our transverse emittance is actually about the same as a Gaussian beam. A lot of this is we have, a shorter or a longer rise and fall time than we really wanted to get at the end of the day. It doesn't come up and it's not a perfect flat top, basically. And these fluctuations here on the top will also increase the emittance a little bit. However, when you look at the slice emittance, so transverse emittance is normalized or is averaged over the entire length of your electron bunch. If you look at the slice emittance, which is your transverse emittance at every point in time along your electron bunch, what we can see here is that there's a very strong peak of emittance that's really contributing to a lot of what we're seeing over here. But across the bulk of our beam, right in the center, which is what we would want to use in the undulator later, our DCNS beam actually has a much flatter emittance profile. On average, sure, a little bit higher than the Gaussian, but this flatness means that there's more linear space charge forces and potentially much more productive X-ray generation later down the line. Yeah, these are slides that were important for the accelerator directorate, but not necessarily for you guys. Basically, how this is actually important for you. We have all of the, UV optics set up, but in order to actually get electron results, we really need to integrate the carbide laser with the safety systems there so that it can actually go to the cathode. It's allowed to go to the cathode and find time on the accelerator to do this experiment. So we have all of the laser work more or less done, but we have to do some stuff administratively, really, to end up actually getting the electron results and being able to experimentally verify some of what we're seeing here. Yeah. So in general, I talked a lot about this flat top for LCLS and LCLS2. The main takeaway here really should be that you have your DCNS. The DCNS method is a way that you can create narrowband pulses from broadband pulses, while also simultaneously shaping in this picosecond regime where there wasn't any sort of shaping techniques before. And that really is like a critical part of it, is that it actually opens up this whole area for you to be able to shape with it. It's complicated. It's hard to use. Adding the phase that you need is not necessarily something that is an easy, like an SLM or a Dazzler, etc. But it makes it viable and possible to do this and also carry out, nonlinear experiments or high power experiments, etc. It's not just this niche case of shaping. So. All right. Any questions about the experimental side of things?
Randy, thanks a lot. I think there's a couple questions. I posed generalist questions, of course, I know the answer. And I'll text the question, so maybe I can read them out loud if you want to.
I see it. I'll read it. Why do we need picosecond pulse for the LCLS2? What if the UV pulse is in femtoseconds? So great question. The short answer is we need a picosecond pulse because that is what the documents that we gave the government saying what we would produce said. That's kind of a cheeky answer, though. In general, you need a picosecond pulse because you can create an electron bunch with a femtosecond pulse, and there's actually been some studies that have shown that if you create an electron bunch with a really short, like 50 femtosecond pulse, then you create an electron bunch that it spreads itself out with space charge forces, and it's something that you could potentially use down the line. However, that's kind of just the theory that is there. The picosecond duration pulse allows us to create our electron bunch in a way that the space charge forces and surface charge forces of the cathode have less effect on distorting your electron bunch's shape as it comes off the injector. It's a much more linear process. It's controllable. I mean, also a lot of it comes down to the, just the design parameters of the injector. If the injector gun itself and the RF fields and all that were designed differently, maybe the laser would change to produce similar X-rays. It's likely that it would be that way. For LCLS2, it's partly just because it's been designed like that for a long time, and partly because this is a very linear regime to work in. Any highlights on top of that, Sergio?
I can add a few things. I think you're right. Yeah. You want to generate this cigar looking like electron beam, and so to reduce space charge effects, you kind of have a cigar like looking like laser. So that's the mapping. You need to put all these electrons, and so it's a space charge calculation, as Randy said. Now, something really intriguing is what he alluded to as well. This 50 femtosecond or whatever shorter pulse duration is not about 50. It's just depending on the charge, but that's called the blowout regime. The blowout regime means just throw in a pancake of a laser and let the space charge create the cigar. That's not something that traditional accelerator physicists, meaning career accelerator physicists, like to play with in these facilities. It's something that Randy and Jack, maybe we could one day, if we have a laser in Sector 0, just try out. I know some people would want to try out, but it's politically loaded. Some people just don't believe in the blowout regime for facilities, but it could work. And if you're more curious about that regime of photoemittance where you actually crank up the space charge to, at the end of the day, get the cigar looking like electron beam, it's called the blowout regime.
Yeah, it's really cool. I like the theory behind it. I totally understand why it's not necessarily accepted, because you're relying on the electrons themselves to basically shape it instead of just trying to directly create it from the get-go. The other thing that is just kind of an important point here, is that if we want 20 picosecond long electron bunch, the emittance off the photocathode scales with your number of electrons or number of photons. It's a percentage of your photons become electrons, which means that your electron bunch profile more or less tracks exactly with your laser profile. So if you want 20 picosecond electron bunches, you need 20 picosecond laser pulses, unless you start working in the odd regimes like the blowout and stuff like that. So Does that answer the questions you have? Any follow-ups there?
Thank you. That makes sense.
All right, nice.
Wait, sorry, just a question. But
Yeah.
the blowout regime has been shown for like DC electron guns. So what would be the difference then for facility? Like,
So one of the things, and I'm not super familiar with how it's been shown for DC electron guns. For all of the XFELs that are out there, X-ray free electron lasers, they use RF injectors rather than DC, right? Because you end up with much lower emittance off your electrons, which is a very hard requirement of your X-ray generation. Also, I'm not entirely sure how it's been proven in the DC gun regime, but it hasn't, like Sergio was saying, it's politically charged. It's something that hasn't necessarily been tested for these. In theory, it probably would work like that, because I think the paper that I'm thinking about was studying the RF injector dynamics. I'm not entirely sure. Is it? Oh, interesting. Didn't know that.
Yeah, it's just simply accelerator. I mean, facilities. Just think about it. People are extremely conservative with facilities that cost $1 billion. You know, they're really, really conservative. They don't want to test anything new. The newness should happen with the X-rays at the hutches. Everything else, nobody wants anything new. But there's also questions on scaling. Yeah, so I don't think it's totally settled. When you have to work with nanocoulomb, like some of these poses are sometimes going to be nanocoulomb level electrons. It's not easy to control space, the control electron through space charge. It's kind of relying on instabilities to control it, right? So I think it would be neat to try it out. It would simplify a lot about these shaping techniques, but yeah, that's as much as I'll say.
Yeah, I also imagine, well, I mean, if there's XFELs and like, I didn't really know that there were XFELs super focused on the blowout regime. I knew that. Are they like large user facilities, or are they more?
No, the ASUC XFEL is this XFEL that is not yet an XFEL. It's based on inverse Compton scattering.
Oh,
the longest story. So they can afford the risk because they don't have a real user base. It's not DOE facility.
gotcha. Are there user facilities that have? Okay, because that's what I was focusing on there, and a lot of it comes down to they just don't want to take the risk, and the reliability for it hasn't been shown properly.
Yeah, exactly.
So
you don't want to mess with the first and foremost component of an accelerator, right? Like it's just that's sort of the level of conservativity that people take. Yeah.
Wait.
Yeah. Go ahead.
Sergio, I think there's a user facility on inverse Compton scattering in Munich, but do you know what that one is based on?
Yeah. So when I mean user facility, let's talk about scale, right? Like SLAC hosts about 600 users a year. This user facility is more like people like us might come for a month or two. So we talk about a few groups a year, right? And it's more about testing the scaling and emission. All the ICS, all the inverse Compton scattering sources out there are incoherent. So you can really, it's the same sort of math that you've been doing. You would have to bunch it in attosecond microbunches in order to get coherent ICS. There's more of an R&D effort where you guys remember LCLS is not built to do science on the machine. We do it incidentally. LCLS is built to do science with the machine, right? So you just want to get to the X-rays as quickly as possible with lowest risk as possible, which explains why nobody wants to try blowout regime, right?
Yeah. You mentioned nobody wants to try blowout regime, but they also, wrote into the documents that they need this 20 to 60 picosecond UV flat top without really determining if that was possible. So another thing how that you'll find out, and potentially others as well, there is generally a pretty large disconnect between electron physicists or accelerator physicists and the laser physicists going both ways. They just don't talk to each other, these two groups, and they really don't have any idea of what the capabilities of one area versus the other are.
I'm going to cut this out of the recording.
I think that that's a fair statement.
Before we run out of time, because some of us have a meeting here.
Damn.
Randy, can you say, I mean, if this technique is so great and we can have all these different knobs to tune things up, why are we doing forward mixing?
Yeah. So, Yeah. So the way that I look at it, right? DCNS is really great. It's very flexible. If you can change your phase reliably of your IR pulses going in, you can create this shaping on the outside. However, it's very hard to change the phase, and it's also indirect. You know, this process, we mix two beams that are shaped in a non-intuitive way for how we want to get to the end. When we mix them together, we get some sort of profile, and we have to do this filtering in order to make it nice looking. For four-wave mixing, you know, and you also go through all these different, you know, crystals and processes here. Four-wave mixing, all of your shaping and conversion and generation is combined into the one step in the hollow core fiber. You're still trying to shape your IR over here in order to shape your UV that comes out. But the magnitude of the shaping that you need to do, phase shaping, is achievable in simpler methods and also much more adaptive methods. You know, there's existing techniques out there to do the phase shaping for four-wave mixing with the amount of phase that you want to add. Whereas here we had to come up with this whole, you know, process, stretcher, compressor, CVBG, to just get this very fixed amount of phase to try and just do flat top shaping. Other things that would be nice for the four-wave mixing is that your output wavelength is also not a fixed thing. Here we're doing crystal mixing, and it's very fourth harmonic exactly. There's no ifs, ands, or buts around about it. But as I understand, changing your pressure or your other components of your process there, you can still get the proper shaping, but go to green or UV or 400, etc.
Yeah, there's a last element too, which is thermal load, right? Remember, I
Yeah.
mean, the numbers that Randy has been quoting, and I can go over people's heads, but this is the highest power photo injector out there in the world. And so you start having distortions in these crystals when you pump them really hard. The gas doesn't suffer from damage, right? So there's limitations in hollow core fibers, but you can pump them maybe an order of magnitude higher before you start seeing distortions. So that's another element here.
Yeah, 3 watts of UV is nothing to scoff at. That is an incredibly high amount of UV power to do it. And all of this is very challenging to do at a megahertz. All of your crystals, when you actually do this in experiment, start expanding and contracting, and the thermal load is awful. It's easier to control that in a fiber.
So how didn't you get a tan, Randy, with all this much UV power?
I literally wore sunscreen. I would go into the lab in the morning, put on sunscreen and gloves and a face mask and long sleeves and work.
That is a lot of power. It's a lot.
Yeah.
What is a lot of power?
Yeah, it's a terrifying amount. Further smooth the modulation of DCNS.
Maybe for you and how to brainstorm a little bit, you know.
Yeah.
So we wanna throw these, you guys, we wanna throw these to the LCLS to photocathode and actually measure these things with the facility, right? Be nice to go back to that and maybe go back to the whiteboard and scratch what we think and think about it again.
Yeah, one thing that I did not happen to mention in this talk, but might be important for you how to think about, we showed that if you do amplitude shaping, right? We're just losing a beam, but it's effectively filtering some of your IR out. You can change your UV profile on the output. If you do this in a controllable way, rather than just a lossy, unwanted way, you can actually potentially control your UV output to something that you want by just adding small amounts of amplitude shaping in your IR. So how that's something to think about. If we do it in the dispersive areas of the stretcher and compressor, you can do it per wavelength. So
it could be an amplitude mask, right? Something that kind of makes your bell shape, you know, have a gradient amplitude mask or something. We could think about it. Yeah.
Yep. So, all right, cool. I will stop talking. Let people get where they got to go.
Yeah. Any last minute questions or anything? Any complaints for Randy? If not, well, Randy, thanks a lot for the presentation. I think it's really useful to go over these details and refresh everybody's memory, and this is going to be good for how as well to kind of catch up quickly.
Yeah. In the future, maybe to a smaller subgroup, if we want to talk about the ULM and CP and stuff, I can bring in that portion of my thesis as well.
Sure. We can break down your thesis in multiple journal clubs.
Excellent. I did a lot, apparently.
Well, thanks a lot, Randy, and happy holidays to everybody.
Yeah,
we'll see
happy
you
holidays.
next
Thanks,
year.
guys. Thanks for having me.
Yeah.